Yeah, let's start. Hi, good evening, everyone. Welcome back to Plan 252. Yeah. Uh, our discussion today, I hope you can start with uh, your group project presentation, and then we can discuss the two assignments 2 weeks ago and this week. Okay. And then we can start with the lecture, this third one. Is it okay? Are you ready for presenting your group projects? So who will start first? I think you're supposed to submit it last night, isn't it? Anyone want to start? Go ahead. I put you into co-host so that we can uh, present also. Oh, go ahead. Lian, you want to present first?
Hello, sir. My groupmates, well, my partner is still not here,
Okay.
but
So your partner, so you want to present at the end?
yes, later na.
Okay. Uh, okay, in that case, I'll put this down. Okay, so the traffic theory assignment last time, I think some of you get 100. You want to present it? The QUK, the fundamental traffic flow diagrams. So that the others can also help. You get 100. Green shield individual. Dennis, can you present?
Hello, sir. What
Yes.
is it, sir?
Can you present your green shield assignment?
This uh, what assignments are the ideal flow network?
No, the green shield one first.
Gradient shield. Okay, sir.
Yes.
I'll find my file, sir.
Okay. How about the others? Aaron, can you present the yesterday assignment, the ideal flow network? While Dennis is waiting, getting his file. Hmm. Are you still there?
Hi, sir. Good evening. Sorry
Yeah.
po. Let me wait. Looking for my documents. Where is that one? this one.
I'll stop sharing mine so that you can share.
Okay, sorry.
Yes, go ahead.
Assignment number 2, sir, or assignment number
Okay, this one is fine also. Oh,
this one, green shield model. Okay, sir. So, actually, this is our first assignment. So from the green shield, we were given the measured already. So we have this given, so the density and then this the speed, and then we learn from sir uh lectures that we can use this equation not to derive for the slope intercept. And then from there, I identify that this one is our negative UF no over KJ, and then this one is our free flow, and then for the jump density, it's actually the inverse. So I multiplied the negative one to this one no, to get no the value for the jump density. And then questions also for this one determine this. So for the free flow speed, so from the intercept no in our
yeah.
generated equation, and then for the jump density, I actually just rounded it off for
Yeah.
easier computation. And then for the calculated values, so again, it's also available in our lecture that this one is just half of this, no? And then critical density is also half of our jump density. And then for the capacity, there's also an available equation, so one half sorry, 1/4 times the free flow and then the density. So actually I write some notes there, you know, how I derive that one. And then for me to visualize no the data, we also learned no, about the flow. We can compute no for the flow rate because we have the density and then the speed. So what I did is I tried to model for the density part. I used the interval of 0.2. Actually, this is just arbitrary, no? You can actually think of other figures, but for this graph not to be achieved, no, the more in I mean the more interval or points, no, the um smooth the curve, no, because that's what we're trying to achieve. And then yeah, so first we were asked to graph no the flow rate versus this space mean speed. And from these model values, no, I also tried to counter check if these values falls also or close no to these values. So from 0.2, we know that it's 0.23, and when I check it here, the flow is correct, no, 0.228, or when you round it off, it's 0.23. Um 0.5 somewhere here. So the value for this, the flow rate no for a density of 0.5 is actually also uh, um within this range. So I created a separate no actually I don't know, sir, how I can integrate no this plots to this, because that's what I'm trying to achieve. So
Just
that's what
right
I
click. Go to this red dot here and then you to right click. I think.
right click,
Yes.
right
And then the chart style. I mean the chart style there.
chart style.
Yes. And you include the line. This is only dot, right? So you need to include the line.
Yes, sir.
So
Actually,
maybe,
sir, I don't know how to do it.
yeah, you just there, that one.
This one, sir.
So scatter chart, you click that, and then there is a menu. No, here in
And
the yeah there. you can select with the line.
Line. Okay, this one.
No, we scatter chart with the line.
Square with
There,
the
the first one, it's something there.
this there.
Yes. Oh, what happened?
I don't know.
Maybe because this is not include all.
The values because
Yes,
it
because you include only two. You're
this
supposed to include
this
all.
this table only, sir.
No, you should include the whole table from 0 to 4.
Okay.
This table, yes. Yeah.
Including this also, sir, here.
Yeah. You just highlight this one, density flow, okay, and then plot it all. You will get exactly this.
Sorry, sir.
Uh,
Can I add data range?
oh,
No.
the range is L, is density, right?
Yes, sir.
Oh, you want the speed and flow?
Yeah, for the first graph, sir, it's flow rate
Okay,
versus
then only these two, uh, M and N.
and this one.
No, only. Wait, I will throw that.
Flow and speed.
Yes, only flow and speed. There, and then you just throw. There. No? Yes.
Okay.
Yes.
Okay.
So that one is incorrect. The same thing if you have flow and density. So you highlight the two columns, which is the density and
This one's just the same of this one is just the same with this one, right, sir?
yes, the same. And this one you highlight this density and flow.
Yeah.
This one.
So for the second graph, again, we were asked to graph flow and then density.
Yes.
This one and this
Yeah,
one.
you vote yes.
Then you will generate this one. And if you want to check also these values also false, no, within the
Yeah, you're supposed to get that circle.
and
Parabolic.
yes, sir. For the third graph, no, we were asked to graph the density versus the speed. So this and
Yes.
actually, yeah, I got this.
This is not correct because
Mhm.
you're supposed to get the other one, the second one.
Insert chart.
Yes.
So,
There. This is the correct one.
okay.
Okay.
Okay, so the correct one is this one.
Yes.
Okay, sir.
So very good. Okay.
Thank
So the others also have certain parameter that is incorrect. UI for Aaron is okay, excellent, okay. But the other I checked, okay, the they use vehicles, but the numbers are not vehicles. So please reconsider your values, okay. Uh, Remember, one vehicles is about 4 meters or 5 meters. So 1 kilometer you divide by 4 meters. So between 180 to 200. That's the number of the jump density, right? So if the value is very different from the reality, so you need to verify your model. Maybe something is wrong with your numbers. Yeah. Can you? Yeah. So, Dennis, you want to present still? Yeah. Thank you, Aaron. How about the latest one, the IFN? You only copy and paste, but you did not answer those questions. No, not this one, the IFN, the second yesterday's assignment.
Yesterday's assignment, sir, for me.
Yes, yes.
Sorry, I haven't submitted yet.
Oh, okay. So anyone submitted yesterday assignment?
I submitted
Yes.
yesterday's assignment.
Yeah, so go.
Yes. I'll share my screen. Let me know if you see it.
Yes.
Yep. So let me open the questions again.
Mhm.
Um, but yeah, basically we were asked to 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 make a random network of
Right.
4 or 5 nodes with 68 links. What I did was just 5 nodes,
Okay.
and um I made sure that the network is strongly connected. So I assigned a random capacity for each link, and I put here the parameters I input in the website. So
Mhm.
the capacity per lane, I just used 1,800, and I used BPR,
Okay.
and I just used what we had in the lecture last week, which is
Right.
the gamma is 15, BPA is 4. So this is the capacity matrix,
Mhm.
and the distance matrix, I just put 1 kilometer, and
Mhm.
40 is the max speed. So the first one is the stochastic matrix. So this was just in the results from the website.
Okay.
And then I have the next question is to calculate the ideal flow for a total flow of 100, a total flow of 1, and the cardinal network, which is
Yes.
the minimum integer flow.
Right.
So for the total flow equals 100, so I just input in the website that the total flow is 100, and this is the ideal flow matrix that I got from there.
Mhm.
And this is the ideal flow matrix for the total flow equals to 1. So for the cardinal network, I just divided each element here to get the minimum integer for each value here. So this
Mhm.
is what I got. And yep. And the total flow for this one is 34. So I just added these values here.
Yes. Did you notice number three?
Yes. All equivalent IFNs have the same coefficient variation of flow
Yes.
regardless of scaling. Yeah.
Yes.
And
So this is very interesting now. So you can find that there is some, even though the average flow is not the same, okay,
mm,
standard deviation is not the same, right? But when
mm,
you divide, to get the coefficient of variation, they are all the same.
yeah.
Exactly, right? So this is very interesting characteristic. And you get some invariance, yes. And
Yep.
then, uh, the travel time.
Yep.
And the last one,
So in here, I've noticed that the current random network is operating at very low utilization with free flow speeds across
okay,
all links and no observable delay or congestion. So 0 minutes delay, and it's achieving the speed
and
that I inputted, and the average travel time is 1.5 minutes. So two policy directions I can possibly think of is just maintain the current operations by preserving the stable conditions through routine infrastructure maintenance and continuous monitoring of traffic flows, or maybe reallocate the available capacity by converting some lanes for other mode of transport like active transport or for dedicated public transport lanes.
super, yeah.
Yeah.
Uh, the did you calculate the efficiency, the far pi index?
I- is I think it's in the is it in the results as well, sir?
Yeah, it's supposed to be there.
Uh,
Okay,
it's
so
um, where's mine?
if you input that, you're supposed to get a far pi
Or,
index. Okay,
let me just open it again. Where's my assignment? Um, oh, it's here.
yeah, you just
Capacity.
copy and paste your
Yep.
capacity.
This is 15, this is 18,
Mm.
and
And
one update
just update.
40.
Okay.
Total flow 100.
There at the bottom, I think you can get the far
Uh,
pipe.
bar pa here.
Yes. Oh, very low. So it's 35%.
Mm,
Uh, okay.
low efficient. Mm.
Yeah, yes, the efficiency is very low. So
Mm.
that means you can still improve, no?
Mm.
So when the efficiency is very low, you can improve by many different ways, okay, to improve the efficiency rather than adding the capacity.
Mm.
But when the capacity is already, when the efficiency is already very high, then you probably want to consider to add capacity. Okay,
Okay.
that I think is very important to notice. Okay, yeah. So overall, very excellent. Thank you. Anyone else want to present your assignment? Okay, so please prepare for your group presentation later. Okay. So in that case, let's go to our lecture. Okay. Today we'll discuss about two things. One is network representation. Okay, and then I'll show you how you can compute manually. Okay, the IFM. Okay. Okay, so you can go to a model in Revolution. So there you can see in transport supply. Okay, so this is the three things that we will discuss today. Network representation, we have lab, okay, network and matrix, and then IFN manual computation. Okay, you can download this. Are you ready? Okay. Okay, so let's start. This is part with what is called graph theory. Can you see my slide?
Yes, sir.
Yes, sir.
Right, good. So, oh, okay. Network is basically about relation. Okay. So the same thing, matrix is also about relation. So what is relation? Okay. Okay, I will skip this part. Yeah. So basically about if you have two things, yeah, A and B, okay, you can have what is called Cartesian products. Okay. So that Cartesian product represents the whole relation that you have between two things. Yeah? It is A and B. Yeah. So the definition of relation, if you have two sets A and B, okay, so binary relation between A and B is a subset of that earlier Cartesian product that represent the relation. Okay, so now if you have a relation A, B, then the inverse relation is B, A. Okay. Now, in matrix, if you do matrix inverse, okay, matrix transpose, that represent the inverse relation. Yeah. Transpose means inverse relation. Okay. So This part I will just skip because this represent the mathematics of that. Okay, you can read by yourself if you want. Okay, now let's start with this. We can represent relation, okay, in list, something like this, yeah, A, comma B, yeah, or adjacency matrix, okay, or adjacency list, okay, or a network. Now, this is the one that we will discuss, yeah. This is the example of network. How many nodes here? 5 nodes, yeah, A, B, C, D, E, okay. And this is how you will write in adjacency list. Okay, so next week you will have a quiz. Okay, so please consider in the quiz or in the exam. Okay, I will not draw. I will give you this kind of adjacency list or adjacency matrix. Yeah, or matrix. Yeah, that's a matrix. This is how you will put adjacency list. Can you see? A colon and then B1. That means this is the flow. Yeah, this is origin, this is destination. Yeah, from A to B, can you see? From A to B, there is an arrow here. That means you will put it this notation. Yeah? From here, can you see? B to C, 1. Yeah, and then C to D, 1. Yeah, D to B. Can you see? D to B. And then E here have two arrow, right? So E will go to A and then E will go to B. Is it clear or not? This notation. This notation okay, is called adjacency list. Okay. So can you write this as adjacency list and adjacency matrix? Yeah, I will give you example first. Okay. So if you have this network here, okay, then you can put it as order of pair. Yeah, so A, comma B, yeah, B, comma C, yeah, and so on. Yeah. So this list of order pair represent the link, right? The arrow here. Okay. You can also put it as adjacency list. Okay. Oh, what happened to this one? D colon empty. What's that mean? From D, it goes nowhere, right? So that means D is a signal. Okay, can you see? D is no outlinks from T. Yeah, so that means this list is empty. Okay, so if you put this into matrix, yeah, adjacency matrix, can you see this? Yeah, the adjacency matrix is a matrix from and this two. Yeah? Can you see this arrow? The row represent the from, the column represent the two. Yeah, so A to B, that is, yeah, there's an arrow here, that's but become 1. Yeah. So next B go to C and go to D, isn't it? So there. Yeah, you put 1 and 1 here. Is it clear or not?
Clear, sir.
Clear, yeah? So C go to E. Yeah. So there is an arrow here, then you put 1 here. Yeah. 1 means there is an arrow. Yeah. Or if there is a flow, that number of flow you can put it there. Yeah. So when we say adjacency matrix, yeah, this is usually binary. Yeah. When we say weighted adjacency matrix, that's usually flow matrix. Now, can you see this? Special. Oh, one whole row of D are all zeros. Yeah. So this is represent that from D, it goes nowhere. That means the fourth row, yeah, all zero, indicate that node D is actually signal. Clear or not? Yeah. So if you use adjacency list, the signal will be identified by empty list like this. Yeah. If you use adjacency matrix, sync node will be a row with all zeros. Yeah. Is it clear? Yeah. So now in your quiz, yeah, I cannot draw this one. So what I will do, I don't do it this way, okay, but I will do it this way. Can you see? So I will use MATLAB notation, okay, like this. Okay, so A equal to 0, 1, 0, 0. What you will do is you copy and paste this in the notepad, okay? And then every time you see the semicolon, you press enter, okay? Then you will get this matrix. Is it clear or not? Okay. In your quiz, okay, I will not show you the matrix like this. This is the one that I will put because this is text file. Okay, so you will see like this, yeah, on the top, yeah. Then what you will do to get the actual matrix, every time you see the semicolon, you press enter, and then it will go to the next row, right? Okay, then you will get the actual adjacency matrix. Is it clear? Yeah. So you separate the list, yeah, into the matrix by each semicolon. You just press enter. Okay, then you get the matrix. So the one in the same notation we use in the IFN online, right? Calculator. So we use exactly the same thing. If you use program, you don't really need to put enter because it automatically they know. The program will understand that this is actually the same as this matrix. Okay. Okay, so now your turn. Can you present this network into adjacency list and adjacency matrix? So put it in Notepad. Okay, those who can get it first, share your screen, you get the recitation point for today. Claim it, huh? At the end of the class, you claim your recitation point, and then you sum, yeah, all the claim that you have, you sum and then put on top, okay? Practice 2. Then we will have a lot of practices.
Can I share, sir?
Yes, go. Did you share? Okay. Can I see? Let me see. Okay. Oh, this is interesting, Dennis. Yeah.
Yes, sir.
So the whole column of D are all zero.
Yes.
What does it mean?
Sync node.
No, it's not
Sync. No. Sorry.
Sync node is a row, all zeros. This is column, not rows. So this is a source node.
Source node, yes.
Yes, a source node, yeah. Can you see? A source
Yes,
node
source node.
is a node that can go out from there but cannot go in.
Yes, sir.
Sync node is the other way around. Can go in but cannot go out. Yeah.
Yes, sir.
Okay, good. So who else can do the adjacency matrix? Adjacency list, sorry. Yeah, that's adjacency matrix already done by Dennis. Yeah, excellent. Yes, Justin, go.
I'll share it.
Yes, share.
There, I think I can zoom it further.
Can wait, okay.
Yeah.
A, B, C, C, E, D, B, and
Oh,
correct, A and B,
oh,
yeah.
it's covered.
So the last one should be small,
Yeah,
correct.
my fault.
Excellent, yes.
Okay.
Very good, yeah. So let's go to the next practice, okay? Uh, now, the next practice, where is the, here, okay. So in the next practice, yeah, let's name it practice 3, right? Can you see? So you get the adjacency list. Can you get the adjacency list from adjacency matrix? And then can you draw? Oh, okay. Two questions this one, yeah. One is to get adjacency list from adjacency matrix. The other one is to get the drawing. Okay, who can do? Uh, those who can do it first, you uh, raise your hand. Okay, and then you will share your screen. If drawing is hard, I've done the program for you. Okay, later. So adjacency list first. Anyone? Yes.
So can I try?
Oh, go.
Uh,
Share your screen. Mhm. A B, B is not B1, but you need to put colon there after B. Okay. Right. You put colon after yes. And then the same thing the others. Yeah. C, D, E, correct. And then E2, okay. C2, C2E. No, there is no C2E. Not correct yet. And why 4? Where it come from for? No, not correct. And yes, okay. So Justin, not correct yet. Place Joshua, not yet. Can you revise? Justin,
Yes, I can share. Okay.
okay.
Oh, this is the drawing.
You did not share yet.
Oh, wait. This one. This is the
Okay.
second one. Then
B,
I
C, D, E,
rough
correct. C, D, correct.
It's a
Okay.
rough sketch of
Yeah, okay. Very good. Yes. Super. Yes, this is correct. Yes. Okay. So now I want to share with you. Yeah, thank you. Thank you, Justin. That's correct. You can claim it. Okay. I want to share with you, okay, the tool for you to throw. All right. So throwing is a little bit complicated. I understand that. So you go here to the lab. Yeah. There is a lab of network and matrix there. Okay. So, okay. You go down here. And this is the lab tool. So you just input this matrix here. Okay. So I can also generate random matrix. And this is the drawings. And these are the pattern of this matrix. Okay. So 8 here represent. So if you put your mouse on top, and you see, you will see this is 1.2. That means cell address. Yeah. 1.2 and then 8 is exactly that one. Yeah. And then, of course, you can play. So you can also load and download this matrix. Yeah. Okay. And you can also change the color if you don't like that rainbow. You can change the color. Okay. Or binary or yeah, the rainbow. And then you can also add the row sum, the column sum, or including the total. Yeah. And then you can hold here, then you will see the total sum there. Okay, I hope this is useful. Now, actually, you can also click here, there. Yeah, you click in this drawing. Yeah. And then if you do click, it will add 1. So before it was 8, now become 9, right? Okay. And I can do right click to reduce it. Yeah. So if you don't like to type, you can also click here to reduce it. Is it nice? Okay. And of course, I can change here directly. Okay. So I can change here directly. Say I put 1, for example, this is 2. So once you change this, okay, example 1, and 1, I put 0. Yeah. Oh, you will see the drawing. Every time you change this, the drawing change, right? And also the visualization of this matrix change. Yeah. And then you can hold control key. Yeah. You hold control key and then hold this one of the node. Okay. There. You can actually move it. Yeah. Nice. Yeah. You can hold control key. So the pole here is C that represent self loop. Yeah. So if you put 0, then the self loop no more. Okay. If this is not nice, so you hold the key, control key, and then you hold one of this there, so you can move it. So I hope this is useful, to represent the matrix and the network and also the visualization, and the sum is there. Yeah. So say in your exam you get confused on how it look like, right? So you just put it here, copy and paste, okay, and you draw it, So of course you can also redraw this one, This symbol is to redraw, okay, so that if you want to redraw. Yeah. And the thickness of this is normalized, so the largest is always the thickest. Okay. So if you click the help, you can see how you use it more detail. Yeah. So of course you can also delete, this one. So you select and then you tell there, you delete. Oh, nice, So I hope this is useful. And you can also add, So you can add like this. You click this one, and then you drag, there. Escape, you got that. Okay, good enough.
Sir,
Yeah.
does
Yes.
it have a limit for the size of the matrix?
Your own visualization. Actually, this is just for visualization. So probably 10, you can still draw. Yeah, up to 10. Yeah.
Okay, sir.
Okay. It's too complicated already.
Yes. Yes, it is. Thank you, sir.
No, the actual limit, there is no limit here. You can add anything. Okay. The limit is your own hardware. Because this is run in browser, that means the limit is in your own hardware. Okay. There is no actual limit. Okay. Hardware limit, yes, but the program has no limit. Okay. But I think 10 is already super complicated. Okay. But at least you can start to see the meaning of, say, small like this, A and B. Oh, this 0, 0, what is that meaning? A is actually a sink. B is actually a source. Can you see that? By putting very small number of nodes, then you start to understand. Oh, this is the meaning of matrix. This is the meaning of graph, like that. Okay. So 0 have meanings, not just 0. So minimum size, of course, 2. Oh, what will happen if I just put 0 like this? Oh, it can. Okay, but that's nothing. It's just one node. So when you click 2, oh, what does this mean? 0, 0, 0, 0. There. Let's put it finally. So all 0, right? The 2 are unconnected network, isn't it? Unconnected, So, but once you connect, so you draw like this, there. Oh, can you see? This is 0, 1. That means from A to B. Yeah, is that correct? Yeah. So then I can draw again from B to A. Oh, there. Now I put there 1. Okay. So now become two-way. Yeah. Nice, So I hope with this you start to understand. You can play with this so that you can start to understand. Oh, this is the meaning of matrix. This is the meaning of network. How you connect between matrix and network. Is this useful? Yeah. Okay. So come back here later on, yeah, if you want. Okay. This is the only lab. Okay. Later on, you can get similar, for example, like this. Okay, such similar pattern and so on. But you cannot click and so on. Yeah, you can still move this. Okay, but you cannot click here. Oh, still can. But this is not really correct. Yeah. Okay. So the click here is not really represent correctly. Yeah. So this only this lab is correct. Yeah. From the next lab is totally incorrect if you click. So come back here later. Huh? Okay, let's come back to our practice. Yeah. Yeah. Now, can you represent this network into adjacency list and adjacency matrix? Oh, anyone who can do it first can show, and then if it is correct, you can claim your recitation. Go, practice 4. The number of nodes is still the same, A, B, C, D, E. Okay, 5 nodes only. I just changed the link, right? And if you notice here, there is no sync, there is no yes scan. You want to share your screen? Okay. Okay, let me see. 1, okay, that's correct. Oops, no, you missed one. From B to E. Yes. Okay, that's correct now. Okay, okay, very good. Okay, so who else can do the adjacency list now? Adjacency list of the practice 4. Okay, please go. Joshua, share your screen. Let me see. 1 is E correct, E correct, D to be correct, A to E. Yes, excellent. Yes. Okay, can claim, yeah? Okay, let's go to the next practice. Is it okay? Practice 5. Oh, so this time, okay, I give you the matrix. Okay, you give me the adjacency list and you throw the network. Okay, so where to share? See? So I give you the adjacency matrix. Okay? So you give me the adjacency list and then you throw the network. So those who can do it first, you can claim your recitation. Yes, can. CE, correct. D, that's correct. EA, yeah, correct. Very good. Okay. So, okay, one more. Who can draw this? Oh, you can draw in that tools a while ago. All you need to do is copy and paste the network. Okay. Yeah, Justin, go. Show. Oh, nice. Okay, this is nice. This is important for you to see the network. Okay. Can we go from A to D? Yes, we can. But can we go from D to A?
The cancer.
Cannot. Okay. So this is as an example, okay, what is called component. Okay. So can you see the D and C in this drawing? Yeah. D and C represent a strongly connected network. From D, you can go to C and vice versa, right? Between D and C. The same thing between A, B, and E. Can you see this drawing? Okay, can you from A, B, and E, they are also strongly connected. So a sub strongly connected sub network, okay, which is strongly connected, this is called component. Okay, so in here we have two components, right? We have A, B, E, and you see the drawing, okay? And then we have D and C as another component, okay? So A, B, E is a source component, okay? DC is a sink component, yeah? Why is it source? Because from this component can go to other node, but cannot come back, right? So why this is sink? Yeah, D and CD is a sink component. Why? Because once you enter this, you cannot come back, cannot go out. Okay, so a while ago you learn about source node, sink node. Now you start to learn about source component and sink component. Can you see that? Yeah, notice, yeah. So, and if you look at the matrix, yeah, you cannot see because they are component. You cannot see. Oh, there is no zero there, right? There is no one row is a zero and one column is zero. You cannot see that, okay? Because they are component. If it is sink node or source node, yes, you can see. Yeah? One row has the zeros in the matrix, but component you cannot see. Yeah. So you need to draw in order to see. Yeah? Or there is an algorithm to compute that. Okay. Okay. So let's go to the next point. Okay. So when we say, can you see my slide? Okay. So when you say strongly connected network, okay, so a network is strongly connected if there is a path. Okay, so you can go from any node to any other node, right? Okay, this is very important properties of network. Yeah. So when people go somewhere, there must be a way to go home. Yeah. So in graph theory, this property is called strongly connected network. Yeah, the matrix. Yeah, if you have uh, adjacency matrix, okay, with this property, this is called irreducible. Yeah, you cannot define irreducible mean you cannot define. Yeah, irreducible matrix. Yeah, so integrated. Okay, so now in this example, I have three networks. Yeah, network A, network B, network C. Okay, so which of this network is strongly connected? Yeah. So if you look at network A, okay, this is actually not strongly connected. Why? Because there is a sync node D here, isn't it? And then there is a source node A. Yeah. So a network that has either sync node, source node, sync component, source component, or unconnected, okay, they are called reducible. Okay? So this is irreducible, okay, it is strongly connected. Okay, so but when you have it reducible, okay, that means either unconnected or weakly connected. Is it clear or not? Yeah. So network can either reducible or irreducible in the matrix. Okay. If it is irreducible, that must be strongly connected. Okay. But if it is reducible, that can have two possibilities. One is unconnected. The second one is weakly connected. Okay. So weakly connected have four possibilities. Yeah, weakly connected have four possibilities. Either you have sync node, source node, sync component, or source component. Yeah, is it clear? Now, in this second example here, you have source node here and sync node, yeah, in the end, right? So this is weakly connected. Okay, and the last network, C here, this is strongly connected, yeah, because you can go from any node to any other node. Yeah, this is the one that's strongly connected. Yeah, and not only that, yeah, actually this network is interesting. Okay, why? Because the flow, the total flow in is equal exactly with the total flow out. So this is ideal flow network. Yeah, yeah. So the node C here is interesting because the network flow is also balanced. Yeah, the flow are conserved in each node. The total inflow is equal to the total outflow. Yeah, this type of strongly connected and the flow is balanced. This is what is called ideal flow network. Yeah, IFN. Okay. Now, a component, okay, is a strongly connected sub-network. Yeah, this is the definition of a component. Yeah. So sometimes we call it SCC, strongly connected component. Yeah, that's the same thing. Okay. So how about this one? Yeah. In this example, this is strongly connected, right? From any node, you can go to any other node. Yeah. Network A is strongly connected. Okay. Now I remove these two links. Yeah. Now I have two components basically. So this network, yeah, B is unconnected. Yeah. So is unconnected. Network C here is connected, but this is weakly connected. Why? Because from DCE can go to ABF, but cannot come back. Right? So there are two components, yeah, ABF, which represent the sync component, and DCE represent the source component. Is this clear or not? Any question up to here? Yeah, reducible can be unconnected or weakly connected. Yeah, and if it is irreducible, must be strongly connected. Okay. Okay, with this example, now you do a practice. Yeah, this one, I give you the note. Okay, let's do the practice. Can you identify the component in this network? Anyone? You just say. Yes, Aaron.
Sir, nodes A, B, E, and then nodes B, C, D.
And one more.
Mm,
One more.
A, B, E, B, C, D.
You remember in set theory, a
Mm.
subset can be also the whole set. Okay, so the whole nodes here, A, B, C, D, E, they represent one component also.
Okay.
Okay, so so the network is strongly connected. Okay, then you will see, the two component, that's correct. Okay, the whole network is strongly connected. That means the whole network itself is also a component. Okay, is that clear? Yeah. How about this one? Can you identify the component and what is the type? Anyone? Okay, Lian.
I didn't realize my mic was off. But the components are ABE, which
Okay,
is
one
strongly connected component, and
more.
then
Then
CD, which
CD.
is sync component.
Yes, this is strongly connected. No, component is always strongly connected.
Okay.
Okay,
Mm.
so by definition. So,
Oh,
but what is ABE in here in this the whole network? ABE is
uh, it's a source component,
yes, and then DE, a CD
a sync component, sir.
component. Yes, very good. Okay, excellent. Okay, so next, yeah, this is the answer. Yeah. So next practice. Can you identify the sync component? Anyone? Is there any sync component here?
It's
Yes, please.
BCD,
B.
BCD,
Oh
the
yeah,
sync
BCD.
component.
Sync component, yeah. So if BCD is a sync component, is there any source component? So
The source node.
yeah, there's a source node, yeah, that it is E, right? Okay, you notice that. Very good. Okay. Yes. So yeah, this is the explanation. Okay. So you can get that. I hope this is clear enough. These practices. Is this helpful? Okay. Let's do it again. Can you identify the source component? Anyone who did not have recitation today yet? Which one is the source component? Is there any source component? or this is strongly connected? Anyone? Yes, Justin.
It's nodes ABE, sir.
ABE is a source component. Is there any sync component?
No components, sir, but sync nodes.
Sync node. Which one is?
It's D.
D. Excellent. Okay. So clear, yeah? Okay, so how about this one? Can you identify the sync node and the source component? Mhm. The sync node is easy, right? D. Okay. How about the source component? Anyone? Yes, Ken.
Nodes A, B, C, and E.
Yes. The four of them create a component because they are strongly connected, right? Okay. Excellent. Yes. So, is this clear? All these practices helpful for you? Yeah. Okay, this one. Can you identify the source node and the sync component? Yeah, I just reverse. Yeah. So the source node is anyone? You know it or you don't know?
Node D, sir.
Yeah, node T is the source node. And then the sync component is component is not always three. Yeah? Can be any numbers. Anyone? Which one is the sync component? Yes, John. John.
It's A
Hmm?
B C E.
ABCE, yes. The ABCE is the sync component in this case, yeah? Very good. Okay. So, how about this one? There's no answer there. So, which one is the source component, sync component? Anyone? Justin again, yeah?
I think I'll try, sir.
Yeah.
The sync components are F and G.
Which these are the three components. Yeah? F, G is a component, A, B, E is a component, and then
Yes.
C, D is a component, and then D, H is a component, and then the three of them, C, D, H is also component, right?
Yes, sir.
So now question is, which one is the source component, which one is the sync component?
F and G are sync components.
FG is a sync component. How about the source component?
Source. I'm getting confused by the arrows. I'll give it to the others.
Okay, who can find the source component? Yes, Ken.
A, B, E.
Yes, ABE is a source, yeah. So source mean can go out, okay, cannot go in. Sync mean can go in but cannot go out. Yeah. So when nodes, okay, form a component, they can be represented as supernode. Okay, as if they are just one node. Okay, that's how you represent in the network. Okay, so we finished this one. Any question, any discussion? What did you learn? Tell me, give me feedback. Yes, Justin, what do you want to say?
I have a question
Oh,
regarding, wait, let me backtrack to the PDF.
okay.
Uh, ah, about weakly connected networks.
Mm-hmm.
Is there still a possibility that all nodes are connected, but it's still a weak connection?
Yes, so remember, we divide into two, okay? One is reducible and then irreducible. Maybe I need to put it in the notepad. I'll find a notepad. Notepad there. Okay. Let's put it in the notepad to summarize, yeah? Okay. So you divide into reducible, okay, and irreducible. Okay. So irreducible means strongly connected. Okay. Reducible have two. Okay. Weakly connected and unconnected. Okay. Yeah. So now make it bigger. So weakly connected, okay, you will have either source or you will have sink. Okay. Source you can have either node, okay, or you have either component. Right? The same thing. Yeah. So if you have sink, you will have exact the same thing. Yeah. So weakly connected, four cases. Yeah. Source node, source component, sink node, sink component. So if you look at Wikipedia, what is the meaning of weakly connected? Okay. They define it this way. Okay. They define it without arrow. Okay. If you see the network without arrow, this is weakly connected, yeah? And they are connected, but with arrow, okay, they are not connected. That is weakly connected. Okay, let's find. Define weakly connected graph. There. Yeah. So weakly connected graph is a directed graph but exists between two vertices if you ignore the direction of the edge. Okay. So if you ignore the direction of the edge, they are connected. But once you put the direction, they are not connected. That is called weakly connected. Yeah. You see, yeah. So I hope this is clear.
Yes, sir. Thank you.
Yeah, thank you. So anything else? Any discussion? Okay, if you still have some doubt, you can discuss with me. Okay. Is it super clear? Really? Okay. So with this, now let's go. Okay, that's the summary. Yeah, let's go to the next topic. Okay, which is computation of IFN manually. Okay, so you go to the next slide. Yeah, I hope this is clear enough. I give you a lot of practices also here. Okay. Of course, this practice is not as simple as earlier. Okay, you need pen and paper or calculator. Yeah, at least. Yeah. If you want to use Excel, that's fine. Yeah. So in this lesson, you will learn how to compute IFN manually only using paper, pen, and calculator. Yeah, of course, the number of nodes is not that big. Okay, you can calculate. Okay, let's discuss first what is definition of IFN, what is the characteristic, and how you compute manually. Huh? Okay. So what is ideal flow network or IFN? Yeah. It's a steady state relative flow distribution in a strongly connected network, okay, where the flow are conserved. So you get the term here, irreducible, that means strongly connected, yeah. And then pragmatic, that means the flow are conserved, okay. So it comes from actually Markov chains, yeah. It Markov equilibrium. Now, later on, I will show you that this is really indeed equilibrium. If you change a little bit, just a little bit, it will not happen. Yeah, later, yeah. So, and you can represent this either by network, so directed graph, okay, or matrix. Yeah, when we say network, that's called the graph or directed graph. When we put the graph, that means undirected. Okay. So here, so IFN is a spatial directed graph where the matrix is irreducible pragmatic. Yeah, in the jargon of graph theory in the network, we said this is strongly connected in the network, and then the flow is the total inflow is equal to the total outflow in each node. Okay, so in terms of matrix, you will see this is irreducible pragmatic. Okay, so can you distinguish the meaning of pragmatic is actually total inflow equal to total outflow, yeah? And then when we say irreducible, that means strongly connected. Okay, so that's it, okay? So very simple, right? Just two words, irreducible pragmatic. Okay, so this is super interesting because many useful application. Yeah. So in this class, of course, we will use it only for transport. Yeah. But in reality, IFN can be used not just for transport. Okay. It can generate music. It can generate text. It can generate image. It can do for automation. It can do for industrial ecology, can be used for politics and so on, yeah, and also for medicine and so on. So there are many applications of IFN, not just for transport, yeah. So the code is available here, yeah, and you can also check the for transport. You can see the code is available in GitHub. Yeah, there is also IFN Excel add-ins is freely available in Driver 2. Okay. And then there's also HTML version. Yeah. Again, it's accessible in mobile phone. Yeah. And there's MATLAB experimental version. Yeah. So some people also develop it in C++. Okay. Not complete. I think Professor Yukari in Japan also develop it in C++ version. Yeah. So why we want to use IFN? Yeah. Again, IFN itself is very general. Okay, not only for transport, but originally IFN is used for traffic. Yeah. So that's why, yeah, the metaphor, okay, the naming convention is still using transport. Yeah. So we use flow, we use congestion, yeah, we use pragmatic, irreducible. These are transport jargon. Okay. So if you are in biology, you want to apply IFN, then you need to learn the jargon of transportation. But you are in urban planning, so there's no problem with that. Okay. So as long as your problem at hand can be formulated as flow equilibrium in a strongly connected network graph, then you can consider IFN, okay, for your modeling tool. Okay. in fact, we can connect this IFN with the LLM, and then it create automation and multi-agent system also. Yeah, that's the other deviation of application of IFN. Yeah. So what is the advantage of using IFN? Yeah, it's a balance. Yeah. So the flow are conserved and it is a steady state solution. So that means long-term stable equilibrium. Okay. And mathematically, it's based on Markov chain and maximum entropy principle. See, using this, you can calibrate using very minimum data. So we call it parsimony. That means stingy. Yeah, little only you can get. Yeah, you can change the adjustment of the flow, and ideal traffic assignment is practically based on network structure alone. Right? You can notice, yeah, last week you have the assignment. Okay, what is your input? The input is capacity matrix, link, distance, and then maximum speed, isn't it? So these are network structure, topological. Yeah. So, and the mathematics is very sound, and it has a way to compute the Nash equilibrium and system optimal, yeah, based on the congestion. Now, of course, this is not panacea. Yeah, you cannot modeling everything using IFN. Yeah, so you cannot use IFN as modeling metaphor if your problem at hand is not system in equilibrium. If your problem cannot be represented as flow in network, or if your network is not connected, so unconnected, you cannot do. Yeah, weakly connected you can transform into strongly connected, but unconnected you cannot. So these are one of the weakness or limitation of IFN. Yeah. So IFN has 4 axioms. Yeah. Irreducible, that means strongly connected. Yeah. That means that the system is closed. Second is pragmatic, that means conservation, yeah, of the flow, balanced flow. The third one is Markov, that means there is a stochastic local information. In each intersection, you need to decide where to go. Yeah. Not the global. Yeah, it's a local information. And then it's a long-term equilibrium or steady state. Yeah. If any of these axioms or assumption is violated, you cannot use IFN. So it's very strict. Okay, so it's very important to show the limitation in front so that you will not use it if it is not this axioms. Yeah. The invariance is important, isn't it? So then what is the characteristic or the properties of IFN? Yeah, of course, because these are the requirement, so irreducible. Yeah, it must be strongly connected. Okay. The second is flow preservation. Yeah, these two are the by definition. Okay, but there are a few other characteristics that is very important. Okay, one is relative flow. Okay, the flow in IFN are relative flow. They are not absolute flow. So in order to make it absolute flow, you need to hook, you need to anchor with certain data. Okay. Without that, you can consider this as relative flow. Okay. The one that you get the assignment yesterday, okay, you will produce equivalent IFN, right? So you can scale up and down because they are relative flow. Okay. The most important is they need to preserve the stochastic probability. Yeah. The stochastic matrix must be exactly the same. Right? You can scale up and down, but the stochastic must be the same. Second is the network must be all have positive link flow, cannot be zero. So that means fully utilized network. Yeah. Next time when we discuss data structure and utilization, you will get more detail about this. Yeah. But right now, you just remember link flow must be all positive. Cannot have zero, cannot have negative. Yeah. So if you put like this, for example, I put this X here and Y here and the Z here, then can you see this? The because of pre-magic, yeah, the sum of inflow is equal to the sum of outflow, isn't it? That means if this is Y and this is X, then the output must be X plus Y. Can you see that? Yeah. So, and then this is Z, right? Going here, going down here is Z. That means in this node, you will get Z plus X plus Y. Then the output is exactly that. Okay. And then when you split this X, Y, Z into X, then this must be Y plus Z. Yeah. So the pragmatic help you, okay, to find the flow. Once you have these numbers in variables, then you can plug in the number. You can set the X and Y and Z. Yeah. You will always get IFN. Is that okay? Clear or not? Now, the meaning is important. Yeah. If you want to apply IFN, okay, you need to remember irreducible pragmatic. What is the meaning of irreducible? Yeah. Irreducible means there is a feedback loop. Okay. That means long-term system thinking. So if you want to apply system thinking, you can use IFN. The most important is integrated, unity. Yeah. United. Yeah. Wholeness. Okay. So I can apply IFN to do morality, yeah, without religion. So by implying the feedback loop characteristic of IFN, okay. So because IFN is irreducible or strongly connected, we can actually separate them into cycles, yeah. So you can check the paper signature of IFN, okay, that is in archive, I think. So that is more detailed. Yeah, we can represent IFN into strings. Yeah, from there you can separate into cycles and so on. Yeah, that is the application is not in transport, so I will not discuss it here. Okay, but IFN is very deep. Yeah, we can have one semester, 3 units just for this one. Anyway, so these are example of strongly connected network. Yeah, so by definition, yeah, equivalent relation, yeah, is actually strongly connected network. Yeah, transportation network is one of them. Communication network is also one of them. Yeah, and in group theory, you have closure relation. This is also strongly connected network. Okay, you can apply IFN as long as it is strongly connected network. Yeah, and then the second characteristic is premature, right? Flow preservation. Yeah. How do you see that? Look at the sum. Yeah. The sum of row and the sum of columns here. Yeah. So they have the same pattern. If you see the sum of row and the sum of column have the same pattern, okay, then you will see this is premature. That's why I put these numbers into color in that lab a while ago, the network and matrix, yeah. So that you can see the color, very easy, you can distinguish this is premagic or not, yeah, because the color pattern must be the same. Is that clear? Okay. So what is the meaning in real life when we want to use IFN? Okay. What is the meaning of premagic? Yeah. That means system in equilibrium, yes, steady state. Yeah. But if you want to use it in real life, that means justice. Yeah. Fairness, equality. Okay, in economic term. So balance. Okay. So that's why because of this meaning, you can apply IFN for many other application. Yeah. outside the transportation. Okay. Okay. Now let's do IFN manually. Okay. Let's do IFN manually. Okay. The technique is very simple. Okay. This is useful for small network. Okay. Usually I use this in paper, yeah, and pen. So what you will do is you set the origin node, any. Okay, you choose any arbitrary node as your starting point, and then you set the any flow. Yeah, for example, I put 100. Okay, and then you check if it is a single link node. Yeah, if a node has only one in link and one out link, the flow will continue. Yeah, unchanged. Okay, but if it has multiple in link, you sum. Yeah, all the incoming flow at that node, and then if you have multiple outlinks, then you distribute the total inflow among the outlink based on the probability. And the probability is outlink probability, not in link. Is that clear? Okay, I give you example. I think we discussed this last meeting. So I put 100 here. Okay, and let's assume equal probability. So you get 50-50, right? Assume equal probability, you get 25-25. And then, okay, again, the 25 you divide by 2, you get 12.5. Okay, and this is the only one link and one in link and one out link. So this is continue. Yeah, and this is already IFN, yeah, ideal flow network. Okay, but they are not integer yet. So if you want to make it integer, you divide by the minimum. So you will get this one. Yeah. So the two network with this E and F are already IFN. Is that clear? Okay. If this is clear, I'll give you one example. After that, we do practice. Yeah. So how about this one? Yeah. When we said cardinal network, that's minimum integer. What is the ideal flow in this case? Any idea? Yeah. The minimum must be 1, isn't it? So I put 1 in here. Okay, let me throw here. So what happens if I put 1 here? A, B, I put 1. But because of the premagic properties, that means going in is 1, going out must be 1. Right? How about CA? CA must be 1 also. Correct? Huh? Easy, yeah? Huh? So how about if I put 2? You can put 2 also in here, also 2. But they are not minimum. Their minimum must be, minimum integer is 1, right? So this is the cardinal network, yeah? So because it not have only one out link, yeah, then the cardinal must be 1 in all link. You see? Okay. So now time for your recitation, okay? Practice 1. Anyone can answer that? Yes, Justin?
There it's 111.
Very good. 111. It's exactly the same. Okay. So you don't be deceived by the shape of the network. Okay. Okay. They are exactly the same. Okay. So 111. So if you put it into matrix, you will get like this, right? Okay. Okay. Next. This is hard now. You need to compute. Okay. I give you time. Okay, once you get it, you share your screen. Yeah, you raise your hand and then you share your screen. Okay, practice 2. Okay, so the only clue here is equal outflow. Mhm. The probability distribution is uniform. Go compute manually. Okay. Whoever can answer first, raise your hand and I'll stop sharing. You share your screen. Yeah, this is one of the issues. So, is it difficult? You want me to explain? Great.
Sure, let me
Yeah.
try.
Okay, you try first. Okay, go. Dian.
Um, I'll
Okay,
share my screen.
okay, I will stop sharing so you share.
Um, just try, sir.
Oh, go ahead. So,
um,
oh, super.
I started with just these numbers first, like what you did, just from 100,
Okay, that's
and
50,
then
50.
I, yep, and then I got the like cardinal, the minimum integer. So the red ones are the integer.
Yes. Yes, super. Yeah. So you can just put any number first. Yeah. So 100. Can you explain how to get it so that the others can also learn?
Yeah, I started with the node A. So
Okay.
since it has two outflows, I assume that these are both equal because equal outflow.
Mhm.
So just a random number 50-50. Then I proceeded to the next node. Then since it has two outflows, divide this incoming node to two and so on until I reach node E, which
Mhm.
should equal to all of these and equal to the outflows of A. So that's 100.
Yes,
Then I
super.
just got the minimum. Yeah.
Yes. Yes. Super. So don't forget to claim your recitation later. So clear, yeah? Is it clear? The others also? Okay. You just set one numbers and then you follow. Okay. Then you can get. Yeah. And check the last one should be equal, right? Otherwise, something is wrong. Okay, this is one of the issues. Good. Okay, next one. What happened? Okay, instead of using a while ago, Lian was using A100, right? What happened if you use link AB? You set number there. Not in node A, but link AB, you put 100. Mm. Anyone want to try? Yeah. Same drawing, you just put there, okay? But now link AB, you put 100. What will happen? Yeah. So if you put link AB as 100 here, yes, please. What will happen? Go.
Sir, so the link in A will become 200.
The link in,
EA or AE will
yes,
become
EA will become 200. That means AE become,
AE is 200. So AB is 100. Wait,
AB is
sorry.
100. Can you share your screen so that we can all
I
see?
sorry. I used my
Ah,
notebook.
you use I'm fine. Okay. Okay, let's use my screen then. You can write here. Yeah. I think all you can also participate right here, right? Can you? So if this is 100, what will happen? Because they are equal probability, this must be AE must be exactly the same as this, isn't it? So this one must be 100. Okay, and this is 100, this is 100. The sum must be, flow in must be the same as flow out. But the flow out is already 100 plus 100, so this one must be 200, correct? Okay, and then what is this? BC now become
50, sir. 50 BC
50,
and then
yeah. So now become
BE is
50, yeah. This one also become 50, right? Okay. And this one become
25.
25. Okay. Yeah. This it become 25. And this one DE
25, sir.
25 continue, yeah. Okay, can you check if this is exactly the same as 200 in E? So 25 plus 25 plus 50, that's 100 plus 100, so 200. Yeah, which is exact. So regardless where you start, it will come back, right? So it's not necessarily you start from EA, so you can start anywhere. Okay, it will come back to the same pattern, yeah. Especially just scale up and down, right? This is if you divide by 25, you will get what Lian was obtaining a while ago. Okay. Okay. Yeah, thank you, please. Next, practice. Seems like easy. It's not. So I give you the stochastic probability. Okay. Now is 2/3 and 1/3 here. How about this one? CB is, because this is the only one, so this must be 1. Yeah. How about this one? BA is the only one, so this must be 1. Okay. With this, can you calculate manually the flow network? Okay. Only 3 nodes. You can do it with paper and pen, or even in here you can throw. You can annotate here. Yeah. In the screen, can you annotate? With different color. Yes, can. You want to share your screen or you want to annotate here? Yes, can. Okay.
Yeah. So basically, I two-third from since A to C is 2/3, C to B is also 2/3, and then the sum of 1/3 and 2/3 coming into B outflow to A is equals to 1. So if you would get the cardinal numbers, you'll just multiply everything by 3. So B to A is 3, A
Okay.
to B is 1, A to C is 2, and then C to B is 2.
Okay. Super. Yes. Excellent. Is it clear what he explained? Yeah. You can just, because this is 2/3 and 1/3. Okay.
Yeah,
So he just put number 2 here and number 1. And
yes.
just follow, right? Because this is 2, then this must be 2. Right? And then this is 1 and 2, this must be 3. And then check if the stochastic is correct. Yeah, it's correct. So
Yes.
by luck, he is correct. Okay. Okay, super. So next practice. Yeah, now it's more complicated, a little bit more complicated. Practice 5. Can you see? So I give you the stochastic probability, okay, one half, one half, one half. Okay, what is the ideal flow network? Okay, anyone who can solve this first? You can share your screen or you can annotate here. My question, is there any way to annotate in this screen? You can try. Yes, see, you can do it. Good. So, how to solve this? You can put any number. Anyone can solve. Yeah, not as easy as before. Yeah. Where you will put your initial number. Say you want to put 100 there. Is it really that hard? Yes. Oh, you want to
Can I
share
try
this?
again?
Ah,
Can I try again?
yeah, okay, you can try again. Oh.
Sir, I'll annotate the question.
Ah, you went on here. Okay, cool.
So I use the one of here.
Okay. So you put 100 there. That means there also 100. Okay.
So
So there
this
is
is
here is 50. Is that correct? Half of 100. This must be 50. Right? This one also 50. Right. But that's not correct. Can you see that? Because 50 going in, 200 going out. Hmm.
so I have this one number.
Ah, now you can start to see the difficulty here.
So I put 100.
Okay.
This is 200.
Okay. Okay, 100 there. So then this is 50-50. Okay, clean it up. This one is how much? 150. So going in is 200 and then 100, 100. Okay. What this one? This one is now become 50-50, right?
Sorry. Okay. So
Don't give up yet. It's only 3 notes. Oh. Oh, anyone can solve this? Can? It's hard, yeah. Okay, can.
Yes, sir. So I started with the input of A. So I assume that to be 100. So
Okay.
C to A is 100. So since C to A is 100, C to B is also 100. And then
You want to share your screen or you want to write it here?
I shared my screen, sir.
Okay, okay. I will stop sharing so that you can share your screen. Okay. And then, so you
And
assume first, which one is the initial?
initial, sir, is C to A is 100.
C to A is 100. Okay. And
Yes,
then,
sir. Since the you will divide the 100 into 2. So A to C is now 50 and A to B
100
is
is
50.
50-50.
Yeah,
Okay.
and since you have the same probability from C to A as well as C to B, so C to B should be 100.
Wait.
And then I added the input to B. 100 plus 50 is 150. So that would be the value for B to A. So to get the cardinal numbers, the lowest factor is 50. So any number that we assumed has the value of 50, such as A to C and A to B, will now become 1. And then the hundreds will become 2. And then B to C, which is 150, will become 3.
Okay, exactly. Very good. Excellent. Excellent, Ken. Is it clear, everyone?
sorry, what was the one up?
Hmm?
So the one half. So
What?
that means that the one half
Where?
is it
This is 1, right?
yeah,
So
because
1.
if from 150 it becomes 100. I've lost in that component, the CB component for like I don't know how
CD,
the
C,
CB
CB.
yeah, so there's the 150 there and it became 100. So
Oh, wait, let me count. This is 50, correct, yeah? Because this is 100, right? And then
okay.
here, you go out is 100, go out there is 100, and then go in is 150 plus 50, so 200. That's
Okay,
correct,
okay. Uh, I
right?
see.
Yeah, that's the trick actually. So if you don't know, you just put X. Okay, you can put X variables and then you can continue with that. Okay, so now, yeah, thank you. Yeah, I hope this is clear enough, but I will show you another way. Yeah, I will show you another way. Okay. This is the systematic way, but more complicated actually than if you do it manually like what Ken did. Okay, so this is the stochastic matrix of this, right? So I put it here. Okay, so now if you want to do it systematically, okay, here what you will do. Okay, let me write. Is my mouse? Oh, here. This is A, right? So this is B, this is C, yeah? This is A, this is B, and this is C, yeah? You remember that. So here you go per column, yeah? You go per column. So that means 1/2 of C equal to the A, yeah? Per column like this, okay? So this is in C, right? So 1/2 of C equal to the A. Yeah. In the second one, 1/2 of A, yeah, plus 1/2 of C equal to the B. Yeah. And then the last one is 1/2 of C, oh, 1/2 of A plus 1 of B equal to the C. Is that correct? Yeah. So if you put this into matrix path, okay, if you put into matrix path, okay, you will see this is A, B, C, right? So A is 0, B is 0, C is half, right? And then the second equation is half of A here, okay? And then half of C here, okay? The third equation is half of A here, and then 1 of B, so 1 here, okay? And this is the actual equation that you will solve, right? But if you notice, yeah, this one is actually transpose of S. Huh? So this is just transpose of S. Okay? So what you want to get is the pi here. Okay? So once you have this equation, you can solve it. Yeah, using polynomial equation, isn't it? Yeah, using polynomial equation. So now this is the actual result. Yeah, the final result is actually 2, 3, 4, exactly what Ken did. Yeah, but 1/9. Let me show you in Excel. Okay, I will show you in Excel so that you will see. Let's do this. You can also try on your own. Okay, let's calculate that. Huh? So I will put S transpose 0, 0, and half, correct? And then what is this? Half and then 0.5, and then this is half, 1 and 0. Yeah. So this is the S transpose. S transpose. Okay, I will put it here. Name S transpose. Okay, so this is the input, right? And this is supposed to be the pi. Okay, so let me put exact the same, yeah. 2, 3, 4. Okay, so if this is correct, okay, the multiplication of this, so let's put this pi. Okay, the multiplication of this must produce exact pi. Okay, let's do that. Yeah? So what you will do is m mole, right? A mole of this one, okay, comma this pi. Okay, I'll just close this. Okay, there, and then I'll put like this, the highlight all, and then check here, and then shift control enter, right? Okay, you can try. Oh, exact, yeah. So this is the green is exactly the same, yeah. So this is exactly correct, yeah. So let's try, okay. This is actually equilibrium. This is the meaning of equilibrium, yeah, stable equilibrium. What will happen if I put 2.1 here or 0.001? C is not equilibrium anymore. Can you see that? Okay. So if you put different value than that, so 0.1, it is not equilibrium anymore. Okay. Can you see that? This will only become equilibrium with this pi equal to pi if this is exactly that number. Okay. So this is a special number, it's not just any arbitrary number. Yeah. This is a special number that represents the equilibrium, stable equilibrium. You understand the meaning of IFN now? Okay. You can try. You try type this one and then you change the number. For example, I change 1. See, it's not. It's not the same. Can you see? This one is not the same as this one. Only when this is 3, then it is exactly the same. Yeah. I hope you understand the meaning of equilibrium. Yeah. It will become invariance. Okay. If you change to any other number for this stochastic matrix, it will not become that number. Yeah. So this is really, really special number for this stochastic matrix. Yeah. That's why this is very important numbers. Yeah, that represent that stochastic matrix, or that represent that network probability. Yeah. If you understand this, then you are start to understand. You can start to appreciate the Fn is not just any arbitrary number. Yeah, it's a stable equilibrium. It's a special number, which is characteristic of that probability matrix. Huh? Okay, you can try. Yeah. And this one can be scaled. Yeah, I can put divided by 9, for example. Okay, 2 divided by 9. Yeah, and then this one 3 divided by 9, right? And this one also 4 divided by 9. So I can put that. Yeah, it will become the same. Can you see that? Okay, if you scale, let me put the scale here. Okay, a while ago is 9, right? So I'll put the scale here, 9. Okay, so this one divided by, well, let's name it scale. Scaling. Okay, so this one divided by the scaling. This one also divided by the scaling. This one also divided by the scaling. Okay. Now I can change the scaling whatever I want. Okay. So I can, as long as positive number, yeah, I can put into 10. See, exact. Okay. I can put into 100. Is exact. Can you see this pattern? This is exactly the same as this one. Okay. But if you add with any number, it will not become the same. You can scale up and down, but you cannot add or minus. Interesting? Yes, you want to say something about this?
Sir, I just want to ask, what's your formula for the M mode?
This one?
The M mode, what was the formula?
Tempo.
The M mode, sir, the for the in your I3,
I3, this one?
yeah,
M,
M mode.
M mode
Okay.
of this one and this one, right? This one, exactly this formula. ST times P pi equal pi, right? So you can try. M mode of ST S transpose times pi equal pi. Yeah, this is the one that we use. Yeah, this is actually Markov chain equilibrium formula. So once you have this, okay, so now let me put it into here. So now you have this. What you will do is you create a diagonal matrix. Yeah, diagonal matrix. Diagonal matrix of what? Of this one. Okay, this one, the second one, and the third one. Yes, Justin, you want to ask something?
Yes, sir. I'd like to ask if the values 2, 3, 4, the pi values are fixed, or does it change with the distribution on the stochastic?
It will distribute. It depends on your stochastic matrix.
So it's like solving this three equations to determine the
Correct. It will be. This is actually called eigenvalue, eigenvector. Okay. So pi is actually the eigenvector of ST. Yeah, this is the right eigenvector. Okay, with the eigenvalue of 1. Okay. So this is exactly eigenvalue, eigenvector equation.
Okay, sir. Thank you. Thank you.
Okay. So can you see my Excel? Right?
Yes, sir.
So I just copy this equal. Yeah, I just put equal here. Yeah, equal, equal. So the rest is 0, 0, right? Okay, the rest is 0, 0. This is, I want to create a diagonal matrix. Okay, based on the pi. Okay. And then what I will do is, okay, so let's put this called the, okay, yeah, okay. Then I will get the F, yeah, the ideal flow matrix, okay, as simple as M mole again of this diagonal matrix, okay, and then this S, okay, so there, okay, you have this, save, control, enter, there. Yeah, this is the result. Okay, let me give, okay, this one. Let me get the sum, and let me get the sum here also, so that you will see, yeah? So the sum of column, right? Copy, and the sum of row, right? let's go to this. Oh, can you see that this is pretty magic? Oh, no. No, why? Oh, oh, sorry. This must be S, not ST. So this is must be transpose, yeah. Transpose of S. Okay. Otherwise, it will not become premagic, isn't it? So let me get it back. This is not premagic, yeah. This is 0.1 and this is 0.35. So this is not correct. So the correct one is transpose. Yeah. Because this is already transposed to the original S. Okay. Shift control. Oh. Okay. Oh, that exact. Yeah, this is the exact value. So if I put this one become 9, yeah, it will become 1. And you will see this is premagic. Okay, I will color it so that you will see. Where is the color? There. Yeah, exact color, the same color. Okay. So I can put any number. So I can put here 1/9 so that the total is 81. Okay. And you will get exact F. So you can calibrate yeah, by scaling. Interesting. Or you want to try this first so that you can get understanding. Yeah. So the scaling is just to get what you want here. For example, I want maximum, I want the maximum flow. This is 27, right? I want the maximum flow to be 81. Can I? Oh, yes. What to do? Oh, I go here. Okay, what if analysis? Yeah, call SIG. This 127, right? I want to put it into 81. What do I change? The scaling, yeah. Oh, oh, so content. Okay, oh, what happened? So if I put this divided by 81, what will happen? Oh, if I put this 27, what will happen? Yeah, yeah, I will get 81 by changing the scale. Yeah, so you can select what scaling you want in order to get what you want. For example, I want, oh, the total flow must be something. Yeah. Mm. So you can get that also. Is this clear or not clear? Something. Okay, let's continue. Next practice. If you have no question. Okay. If you have question, go ahead. Clear. No problems. Okay, so Okay, this is the result a while ago. Okay, how about this one? This is more complex. You can annotate here, or you can put in the any form. Yeah, if we cannot finish this, so it become assignment. Okay. If we can finish, then no assignment. Is it difficult or easy? Just put any number, okay, as your initial value, and then trace the probability. So if I will look at the denominator here, 4 and 3. Okay, if I multiply that, I will get 12, right? That means if I put that 12 there, so it will be then divide easily, probably. Yeah. So let's put this 12, for example. Then this one must be 1/4 of 12 is 4. Yeah. 3 over 4 multiplied by 12. That means 8, right? So this one is 4. Oh, this is difficult. If this is 4, you cannot divide by 3. So you need to increase the value. Maybe 24, that case. Anyone can solve this and share your screen, or you can put it here directly. Where are we? This one, right? 46. So in node A here, yeah, will divide by 3. Yeah. So 1/3 will go here, 1/3 will, 2/3 will go here. Okay. So if this is 2 and 3, this must be 3. So if 1/4 is equal to 3, so this one must be how much? Times 3. So this must be 9, right? So if this is 9 and this is 2, this must be 11, right? Anyone can solve?
Sure.
Yes. Yeah.
I'll try.
You can
Uh,
go here or you want to
I'll just share my screen.
okay, go.
Um, let me know if you see it.
Okay. Right.
Um,
So
so I
you put
yeah,
50.
I just started with 50 here.
Okay.
Then went around. So if this is 50, that must be like 3 times. This one is 3/4. That must be 3 times. So I just put
Yes.
150.
Okay.
And then after that, I just went from
By 3.
to here.
Okay.
C divided by 50 times 2 over 3, and then 50 times 1/3. So
Yes.
16.66, 3.3. And
Okay.
then from here, I
You-
just added this one and this one, so I got 183 and just divided by the lowest.
Yes.
Mm.
And then when you
The red ones are the lowest one. So this one, 2, 11,
11, 9,
9, and 3.
3. Yeah. Very
So
good. Excellent. Yeah. Excellent. Yes. So you just trace, okay, you will get that value. Yeah. Excellent. Okay. So let's go another practice. This time, okay, is now we have 4. Yeah, earlier you have only 3 nodes. Now you have 4 nodes. Practice 7. So given the stochastic matrix, okay, so this one is 1/2, 1/2. This one is 1/4 and 3/4. The other one is all 1. So then you can you find the ideal flow matrix? Yeah. So there is a clue so that you can do it faster. Okay. So you can assign 300 directly to node A. Okay. Can you just practice? Anyone want to answer this? So if you put here, what is this? A to B is 1/2, isn't it? So I will put the stochastic in. So this is 1/2. This one also 1/2. And then D to A. This is the one that 3/4. And then D to B is 1/4. So the others is just 1 and 1. This one is also 1. What happens if you put 300 in node A? So if you put 300 in node A, this is 1/2, 1/2. So how much is this? AB? Yes, Justin. You want to share?
Try by annotating at your screen.
Oh, okay, sure, cool.
I'll just make my pen this color.
Yeah,
So
different color.
assign 300 to node A, which is coming to node A is 300.
Mhm.
Then coming out of A is 150.
Correct.
And also this one.
Yes.
So the tricky part now is what's coming out of B to B.
You don't know.
But since you can do the ratio, you can ratio and proportion 3/4 and 1/4. I did the ratio and proportion of
Mhm.
300 over 3/4 equals to x over 1/4.
Mhm.
I got 100.
Mhm. Yes.
And then so 100, then 150 coming out of BC is 250.
250. Yes.
Sorry, it's a messy
It's
writing.
okay. It's okay. Yeah.
And then
250.
coming out of C to D is
250 plus is 400.
400.
And then you check it is correct, 400.
400, then 300 coming out, and 100 coming out.
Oh, excellent. Yes. Okay. Yes, this is the IFN. Okay. So question, do I need to make it minimum integer? No need. Yeah. This is also okay. Yeah. This is already IFN. Yeah. So, but if you want to make it minimum integer, you can get also. Yeah, just divide it by the minimum. Okay. Now, in the next practice, practice 8, okay, is not as simple as earlier. So, of course, clear all drawings. Okay. So in here, let's assume the uniform distribution, but the number of links is so many. Okay, so I will solve it for you so that you can see. Okay. So even if you add certain value, so this is all uniform distribution, yeah, equal probability. Okay. So I start here by assigning, for example, TA here equal to TE. Yeah, so I put this as 200, 100. Okay. So I put this DA equal TE 100 like this. Okay. And then I check in node A. In node A, I have enter 100. and then I now divide by 4, isn't it? Yeah, so there, this one become 25, 25, 25, yeah. But when I go to node P, I only know this one going in 25, okay? And I don't know this one because there is another going in, but I don't know, right? So because I don't know, I will put this name X. Is it clear or not? Yeah. So you trace, right? You get this one already A, yeah? But this is 25, I know, but I cannot get the actual value of P here because there is another flow in. Okay, so in this case, I need to name X. Yeah. Once I know this is X, then the total is 25 plus X, isn't it? So then you divide by how many links? 3 links. Yeah, so divided by 3. Is this clear or not? Up to here. Yeah. At this point, you start to see we assume first we don't know X yet, okay, but later we will know. Yeah, this is what we will find. Okay. So once you have this, okay, now you go to C. Yeah. Node C, this one is already X, but this is equal. And yeah, this must be X also, this must be X also, right? Yeah, because they are equal probability. Okay. So then we have a new equation here. Yeah. The 25 plus X divided by 3, that's equal to 3X. Oh, plus 25, yeah, plus 25, that's equal to 3X. That is to find the X later. Okay. And then in node D again, we already get this one 100 and 100, and we know this one 25, and we know this one 25 plus X divided by 3, but we don't know this one, E to D. Okay. Again, we don't know this one. So if we don't know, then you assume as a new variable, Y, like that. Okay, now you have two variables. Yeah. ED is Y. Okay. Now by the assigning this pre-magic, yeah, come back, then you will get the equation because you have two equation and two variables. So now you can solve it. Yeah. If you solve X and Y, okay, then you will get everything. Is this clear or no? Yes, it's a little bit more complicated because a lot of links, okay? Yeah. But it's doable, right? Yeah. I mean, uh, why don't we just use the software? The software is already there. Last week you already have it. Okay, you got that already. So you, I just want you to understand that you can do it manually. Okay. Uh, yes, if you don't have time, you want to use software, then you do it. But sometimes you don't have access to software. You only have pen and paper. Then you can still do. Okay. In fact, for me, yeah, personally, I prefer to do manually. Why? To practice my own brain. Okay. So that once I make that, I start to see something different. Yeah? There are new ideas coming out when you start to do manually. Okay. So clear, yeah? Okay, let's try this one. This is interesting. Why? Because, can you see this? There is 0, 0, 0. So, can you solve? Cannot. Yeah, why cannot? Because that is source. Yeah, there is a source and sink. Yeah, can you see this? This is also 0, 0, 0. Yeah, the source and sink. Yeah, in fact, A is a source. Okay, and then C here is a sink node, right? So this network cannot be solved for IFN. Okay, you can try in the software, it will not give you the correct answer. Yeah. So then, how to solve this one? Yeah. Remember this. Yeah. If you have a weakly connected network, okay, you can still use FN, but you need to create either a cloud node or a dummy link to connect the sink and the source. Okay, so this is how I will do. Yeah, so this is uh, the network contains source basin, and sink basin, so not C. So if weakly connected, we cannot compute IFN. Okay, yeah. To connect this, you need to create a cloud node. So I create a new node. Okay, this is a tool help you to create strongly connected network from weakly connected network. Okay, so the theorem of IFN said you only need maximum one cloud node, minimum 0, meaning I can connect directly C to A, okay, but I can also connect with Z. When you put cloud node, that means this is external of your system. So, external node is a super node, represent everything else outside of your system. Okay, so that means now I create a new node here, Z. So, and then the sink, I connect with dummy links to the cloud node. And then from the cloud node, I put to the source. Okay, with this, what will happen? Yeah, this is the original S. Okay, and then now you add one more row and one more column, Z, represent the cloud node. Yeah, and this one is the probability is 1, right? This one also probability is 1. Yeah, can you see? Okay. So now with the new stochastic matrix, you can solve. Yeah, this one is easy. You can solve it easily. Yeah. For example, I can set the node D here to 4. Yeah. Okay, because this one is 4, 4, 2, 2, so that GCD is 4. Right, so I can put this one as 4, then I can solve this one. Yeah, I can solve this to get this result. Yeah. So initially I have this one, I put 4 here. So that means this is 1 and 3. Right? And I can put here 4, for example. I can put 4 here. Okay. That means from there, this one is 5. Right? So 5 plus 3 is 8. So, and then I put this one 8. 8 still continue. And this one is 4 plus 4. Yeah, so exact. Okay. So here, is it clear or not? So if you have weakly connected network, okay, to make it strongly connected, you add a cloud node. Yeah, this is an external node. Yeah, represent outside of the system, and then you connect the sink. Okay, sink basin, that can be sink node or sink component. Okay, to the cloud, and then from the cloud you connect back to the source. Okay, with the same amount, of course. Then you can get strongly connected. Yeah, the software, the IFN transport have done this automatically. Yeah. So if you check, yes, I want to have cloud node, it will calculate to create a dummy links and cloud node and compute. Yeah. But I want you to understand the concept, not just to use the software. Otherwise, it's misleading. You don't know where it comes from, and then you just use, and then you don't know what is this. So that's misleading. Okay? So it's better if you understand slowly, but you understand the actual things. Okay? Is this clear? Yeah. Okay, I want you to practice the next one. This is interesting because it's simple, actually. Look like complicated, but actually simple. Can you solve this one? And this network is symmetric, yeah? So if you have a symmetric network and the probability is also symmetric, yeah, the result is really simple. Anyone can solve this? Yes, Justin.
It's all one, sir.
Yes, it's all one. Yeah, it's really simple. Okay, so you can see if I put one here, one, 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 one. Okay, it will satisfy the stochastic matrix. Yeah, as simple as that. Remember, yeah, when you see something symmetric, okay, and then the stochastic is also uniform, okay, then things must be simple. Okay, yeah, this is all one. Okay. Now, the same network, be careful, I show you this one, seems like simple, okay? But now what happened if the same network, the probability is no longer uniform? Yeah, this one. Okay, this is, I think this will become your assignment. 11, 12, 13, and 14. Okay, this will become your assignment. Is it okay? The answer is there, I know. If you want to cheat, you just copy and paste, okay? But the purpose of giving you assignment is not for you to cheat, isn't it? For you to understand, okay? So I don't need your grade. You don't really need the grade. What you submit, you get 100 anyway, right? You submit it on time, you get 100. But I want you to learn to practice. Is that okay? So 11, 12, 13, yeah, and 14. Yeah, this one is, they are interesting. Okay, 11 is interesting because they are different from here. This is simple. Okay, suddenly you become much more complicated because of different value in the stochastic. Okay, so and then 12 is again uniform distribution. Seems like simple, okay? But if you look at this, okay, if you compute it wrongly, yeah, using x and y, for example, okay, this one, you will not get the correct result, okay? In fact, when you set any value of x, you can, right? But it will not get you the correct result because the stochastic is not the same. So you need to check the stochastic matrix is the same or not. Okay, that's the meaning of this assignment. Yeah, and then the 13 and 14, okay, this is usually in the exam, right? So this is the example in the exam. I'll give you the network, and then I'll give you the link flow. Yeah, for example, YSTC here. Okay, so then you need to answer that. Okay, so this is you need the answer is already here. So you need to try on your own. Okay, so that you get the answer. Okay, and the last technique in practice 14, okay, is exactly similar to for 13, but I just changed this value. Okay, when you change this value, suddenly everything changes. Okay, why? Because now you start to get 0. Okay, which is not correct. Why? Because the link flow in IFN must be positive. Now you start to get that if you make mistake, yeah, you will change the data structure. The network change. If you put 0, that's mean no link in here. Okay, so that is not correct. So I hope using this, okay, you can, yeah, if you set P equal 3, it will change the network structure. When you set the flow, you should not change the network structure. Okay. So with this, I hope you have assignment for next week, yeah, for 11, 12, 13, 14. Okay. And then now is your time to present your group project. Is it okay? Just a short time. I want to know what are you going to do for your group project. Okay, go. Time is yours. Okay, who will do first? How many groups do we have in this class? 3. Oh, okay, go. So group 1. Okay. Who is the leader in this class?
Hi, sir.
Aaron. Okay.
Yeah. So
Okay.
for group 1, we have Miss Balagtas, Sir Beltran, and Sir Buena po.
I think Beltran is out of our class, isn't it?
Yes, sir.
Okay, so ito, yeah, and Dennis. Are you okay?
Yep, sure. Share my screen quickly.
Okay, go.
So this is just a very quick presentation. We haven't done any.
No
Um,
problem. Just the idea.
yep. So let me know if you see my screen.
Yes.
So our chosen location is Katipunan Avenue,
Okay.
and this is the proposed topic, and this is a brief like summary. So since
Okay.
there's a growing number of private cars along Katipunan Avenue, it's resulted in heavy traffic congestion. So this issue is further compounded by the lack of adequate and efficient public transportation, poor traffic management, and increased activity from academic institutions in the area. So like EPD Manila Ateneo and other commercial areas. So
Okay.
this study will aim to evaluate the impact of improving public transportation services and implementing various policy interventions on reducing traffic congestion.
Okay. So what will be the policy that you want to implement?
Currently, it's just in very initial policy, but like, um, let me just present this base scenario.
Okay.
Only have base scenario from the IF network website.
Uh, Katipunan is just one corridor, right?
Yes.
So it's not strongly connected.
When I run the in the website, sir, it says it is strongly connected.
Okay, can you draw later the net
Um,
that we can see?
I think it's still here. Yes, this is the what I exported from OpenStreetMap.
Okay,
And yes,
and down there,
I
can you
think it's yeah,
draw the
yeah,
net?
network is strongly connected.
Yeah. Can you draw the network down? Display network?
Yeah, yeah.
Ah, okay. So you include other part.
Yeah.
So and then what will be the alternative scenario?
We haven't run anything yet, so
Yes, yes.
but what we were just thinking if like we just like prior improvement on the efficiency.
Okay.
Yeah, like because there's a lot of IPS signal traffic in Katipunan Avenue, so maybe we're gonna start with that.
Yes. So if you can make the several traffic signal, okay,
Mm-mm.
in one corridor, so one's green and then the next one also green, the next one also green. Is it possible? That will improve the through traffic, isn't it?
Yes, sir.
Yes. Yeah. Oh, okay. So go ahead. This is very nice. I think you can improve that.
Yep. Our progress is just until here for now.
That's okay. Yeah,
Yep.
that's okay. So then you need to check only the signal timing that
Mm.
currently they use. Okay, just check the green time, how long is one cycle time, and so on
Okay.
for each connection. That's very easy to check.
Yeah.
Yeah. And if you have the one flow data, is okay. If no flow data, I think this IFM can give you the flow already.
Oh, okay.
But the
So
signal
this is
timing.
signal time for intersection. Yeah.
Yes, and be careful that the IFN in the intersection will have full connection, but in reality you don't have that full connection. So you need to
Mm,
detect the intersection.
Hi, sir.
Yes.
Uh, Sir, in relation to that, we experienced some problems regarding the GIS converter.
Oh,
Is it running, sir?
what do you mean running?
The IFN GIS converter application.
Yes. It give you just to shape file,
Yes,
right?
sir.
Yes.
Can we convert that into shapefile
Yes.
using?
Yes.
But
You
it,
can.
it
It
doesn't
can.
run, sir.
It
Can
doesn't
you?
run.
Yes, sir.
Oh, but I think
We run it this afternoon, but
it
we
doesn't
didn't get
produce
any
the correct
shapefile.
one. Hey, it produce. I think that one is in the old, in the old model, right? The GIS converter. If you cannot get shapefile, can you also put it into a JSON, for example? This one?
Yeah, yes, sir.
Yes. How about this example? Is it running?
It's not running, sir.
Oh, okay. So I will check in that case of why it's not running. It used to run.
Mhm.
Actually, we can check it here if you want. So tools, developer tools. Oh, there's an error. Okay, I will improve that. Maybe because I moved to another folder.
Okay. Thank you, sir.
Yes. Okay. And then, how about the next group?
I'll be sharing for our group, sir.
Go. Okay, I will take note. Yes.
Let me just go up.
Okay.
So for our progress, I mean our project, we are going to optimize the passenger flow and network efficiency at Cubao Station along EDSA. And
Okay.
it's a multimodal transit hub study. So the objectives is to describe the multimodal transport network centered on Cubao Station, including spatial layout, modal interchanges, and trip generators. We're also going to predict passenger flow patterns using,
Generator or trip attractor? Cubao is trip attractor, isn't it?
excuse me, sir. I didn't quite
Trip.
get it.
Cubao is trip attraction rather than trip generator. Trip generator in residential.
Okay. So, yeah,
Mm.
we
Okay.
changed part. Okay.
Yes.
Sorry. Then also another objective is to optimize flow through scenario testing, design interventions, and policy recommendations to enhance transfer efficiency, reduce congestion, and improve commuter experience. So for the scope of our study area, Cubao Station, which connects LRT2 and MRT3, and
Mm-hmm.
the area to be considered is an 800-meter radius covering Araneta City, Gateway Mall, Farmers Plaza, and adjacent areas.
Mm.
The model coverage shall be by rail, bus, jeepney, UB Express, pedestrian, and private vehicle interface.
Okay, so what you need is actually you need to have a point transfer between these modes.
Mhm.
Okay, you need to identify the point transfer between this mode. For example, from rail to pedestrian, where they will transfer. From bus to pedestrian, where they will transfer. Again, the same for jeepney to pedestrian and so on. So,
Yes, I
okay.
think we have it down here. Uh, yeah. So this is the baseline and alternative scenario that we have.
Okay.
So for the network configuration, it's still, oh, sorry. For the analysis, for peak hours, we have this baseline data. And then for the alternative, we are redistributing through the demand through incentives. So
Yes.
there's a
So
change.
at the end, you need to put it into one unit, okay? Say pedestrian or
Okay, sir.
person, like that. Mhm. Because you are multimodal, so it cannot become car, right?
Mhm.
So it should be people or pucks per hour.
Okay, yes, sir.
Okay.
So
So
for
one
the
unit.
capacity, it's capacity and supply, it's for the pedestrian per hour.
Yes.
So we have this one. I think the units are just a bit off. But
Yes.
we can recheck it. And
Yes.
its alternative is the same as the base scenario.
Great. Okay.
For the efficiency factors for pre-magic, so for the baseline, frequency and regularity of trips, the transfer from MRT to LRT, escalator queues, number of ticketing
I
vendors, number.
think this will become difficult unless you, this is just assumption, right?
Uh,
Unless you already got the network and then you compute, then you can know the actual efficiency.
I I I think one of our group mates has a data for.
Really? Okay, so you can show
Correct.
Sir, this is just a
Oh
sorry.
yeah.
I was only quick with this, but this is just uh, initial efficiency factors that but yeah, because
right.
you said that you want an
Right.
efficient.
So I guess that's the initial value. That's okay. So once you put to the detail, that numbers will change.
Okay.
70% is very big.
Okay, sir. Yeah.
Okay.
For the alternative, so improve frequency and regularity of trips by at least 5%, and then pedestrian flow design plus 20%, or to make it wider paths, directional signage, frictionless intersections, and fair incentives as an alternative scenarios to
Okay.
increase the demand management by 10%.
Yeah, so this is still in the strategic level. That's fine. Okay.
Yes, and for congestion, we still have to compute for both
Yes.
scenarios.
The same efficiency is also need to compute later on,
Yeah.
Pi and so on.
Yes, and yeah, this is the current state of our
Yes. Good,
progress.
good. Can you upload this in Refoledo?
Yes, we will.
I did not see the result yet. Okay, the third group. Yeah. Yeah, so you can proceed with that. Who is the third group? Ken and Aaron.
Mag-share ng screen, kuya.
Mm.
Okay,
Yes.
sorry. Let me check what's the latest one.
Katipunan lagi.
Yeah. So, we want to actually, sir, assess the traffic management scenarios for Katipunan using IFN. And we are actually revisiting an old proposal, no, to build flyover or Katipunan flyover, no, in the location, I think back in 2016 or back in 2017.
Okay.
Thanks, right. So for sir, for the background of the study, no, so the Katipunan flyover is a proposed infrastructure project under the Philippines DPWH. It's aimed to address no severe traffic congestion along Katipunan Avenue in Quezon City, and this is a critical transport corridor, no, for major educational institutions like University of the Philippines, Ateneo, and Miriam. No, and this has been a long-standing traffic choke point, no, in the area. So for this one, the project involves actually a construction of a viaduct and a flyover. And then the viaduct actually is designed to have 4 lanes. But yeah, that will run approximately half kilometer from C5, no, to Ateneo de Manila University Gate 3, no, near in Miriam College. But for the purposes actually, sir, of this study, we are considering the Katipunan flyover, or the two lane concrete flyover, which is planned from C5 road, turning left, no, to CP Garcia Avenue at UP. And so for this one, the DPWH has emphasized, no, that the project will require the use of approximately 8,000 square meters of UP Diliman's land, no, and that need no negotiations with the university.
Okay.
Next. Okay, so sir, for the objective of our study, so first we want to achieve no three main objectives. One is to measure the current traffic, so it will show us exactly where and why traffic jams happen by comparing real world congestion to the models, no, of the ideal flow. Second is to test solutions or our determined alternate scenarios. So we can see how adding a flyover or even changing a U-turn slots or opening or closing intersection would affect the traffic flow, no, throughout the entire area. And lastly, to provide a data-driven advice, no, so uh, the simulation will tell us which solution works best to reduce the traffic.
Okay.
And then for the research questions, so we have 4. So the first one is more about what is the traffic like now. So we will use the model to measure the current traffic flow, no, pinpoint the exact bottleneck locations, and quantify, no, how bad congestion really is on Katipunan Avenue. And then second, sir, is what happens if we build the flyover, no? So we will simulate the proposed Katipunan flyover to see how it affects the traffic, no, not only for those using the flyover but also for the other vehicles on the road po. And then third, related to do U-turn slots and open intersections help or hurt, no? So the model will test or will help us to test, no, whether the keeping or removing U-turn slots and opening intersections improves the overall traffic flow or will make, no, the congestion worse in the area. And then lastly, what's the best possible solution? So by comparing all the scenarios, no, and then the by using the ideal flow network, it will help, no, identify the most effective combination of improvements, whether it's the flyover, changes to U-turn, that changes the U-turns, no, or the signal timing or other measures, no, sir, to achieve the smoothest, no, traffic flow. So
Hmm.
for our study area, so again, our study area focuses on the traffic hotspot in Quezon City, which is Katipunan, no. And then the key area we are analyzing is the intersection between two major roads. First is the Katipunan Avenue or the C5 road, which is a very busy and important circular, no, road that goes around Metro Manila. So we're looking at the part that passes by several big universities, no. And then second is the CP Garcia Avenue, which is a main road that connects
I,
to Katipunan.
I don't get what you mean by Katipunan Avenue because this is very long until
And
Libis, isn't it?
mhm, sir.
Is that
Uh,
what you want to get or?
uh,
So, sir, will be only limiting the stretch from basically from the UP area up to the intersection
Oh,
near Aurora Boulevard.
oh,
mhm,
So,
no. No, that's only 2 kilometers.
yes, sir. But we would like to test if, again, simulate if we are to introduce a different interventions with regards to the flyover, U-turns, and the signalized intersections in the area.
So that's okay. Uh, the problem is whether you can make it into network. Yeah, because this is one corridor, right? So
mhm,
uh, without making it into network, so this this is just a practice, not so useful. But if you can make it into network, then that's yes, this is important. And I'm not sure. So uh, because Katipunan is C5, right? The majority people will either use C5 or C3, isn't it? With this ETSA. So I'm not sure if you want to include those two or including C4. Okay, that means you ignore the local road and you only get the major road. That's one alternative that you want. Otherwise, if you are only focused in one corridor, I'm afraid it will give you the good answer, but it's biased, no?
mhm,
Because people have no choice in that case. But if you start to see in the whole network, then you start to see the induced traffic. You start to see the change. Oh, if we make this widen or smaller, and how about the other side? Then you can start to see the interactive between network.
Okay, sir.
That's my concern. So please consider.
okay, sir.
Yes.
So we
Oh,
also research, no, for the daily vehicle volume. So according to a research study, no, from the Ateneo University, the daily traffic exceeds 100,000 vehicles, no, with pronounced directional patterns during peak hours. So morning show heavy southbound, no, flow toward Ateneo and Miriam. with 6.6K vehicles, while afternoons see balance high volumes in both directions, so approximately 5,000 to 5.7K.
How many lanes that one?
Um,
4 lanes?
around four,
Or
sir, I think.
4 or 6?
It depends on the segment, sir.
That's exactly the problem. So
Yeah.
the problem is the road is not premagic. There is an imbalance number of uh,
Correct.
lanes. Okay, that is the cause of the actual traffic problems. If you can address that, that's probably better solution than just adding flyover.
I
Okay.
okay, sir.
Okay, because if you can see this number 6,600, okay, that means you only need, say, if one lane is like 1,800 capacity, you divide by that, how many lanes do you need actually? Or say 2,000, okay, that means only 3 lanes or 4 lanes. And right now is already that number of lanes, right? So yes, in the morning is close to heavy peak, but the other one is not. Why southbound is much higher than the northbound? Let's try.
Sir, I think it is because of workers coming from Northern Quezon City trying to get to the CBDs down in the south of Metro Manila, like Ortigas, Eastwood, and Makati.
I see.
So that's why there's a higher number on the southbound side during the morning.
And off to evening.
And on the evening, sir, yes.
Okay. So I did study in Katipunan area long time ago, 2011, I guess. I still have the data. If you need, you can get it
Yes.
from. Yeah. Okay.
Okay, sir.
Okay. So thank you very much. Sorry for late today. Yeah.
Sorry, for
You can,
I think we can
yes, you
skip
can
the
continue
other.
this one. No problem.
Okay.
Yes.
Do you want to continue, Kuya?
Yes, so basically this is the base scenario that we are looking, the current scenario, basically with the U-turn slots, signalized intersections and a closed intersection. But we would like to test, next slide, the alternative scenarios. We have identified five. Again, whether the flyover will be constructed, the U-turns will be in place, or whether the intersections are closed or open. So these are the alternate scenarios that we have identified. But we haven't yet run any simulation for either the base and alternate scenarios, sir. Since we only decided on this topic just last night because with our earlier
Yes.
topic proposal, we had some difficulty and some concerns with regards to our original topic.
So my suggestion uh, to group one and group three, because you are in the same area, do you want to combine into one group?
Answer.
Yes,
It's
sir.
fine by me, sir.
Fine. Okay.
Yes.
That means you will add more alternative scenario, right? The one that you have already, so you just add. Okay. Anyway, you share the same data, so
Yes.
that will yes. Okay, cool. In that case, you combine in that if you like, and 4 person is okay. Yeah,
Okay,
so
sir.
one two groups.
Yep.
Yeah. Okay. Great. So thank you very much. So you have assignment. Okay. And see you next week.
Thank you, sir.
Thank you, sir.
I will post the assignment tomorrow. Not today.
Okay po.
Thank you po. Thank you po.
Thank you.